Hello everyone. We are going to start in a moment. I am waiting for more people if they want to join, and we will start in a couple of minutes. The agenda today is to discuss Kosaraju algorithm for finding strongly connected components in directed graphs. Okay, and also like in these few minutes, if you have anything to discuss, you can ask. Hello everyone. We are going to start in a moment. Okay, guys, if you are able to hear me clearly and if you are able to see the screen that I have shared, please give me thumbs up. Vinay, just 1 second. We are sharing this screen. Those of you who is watching on YouTube, just like hold on for a moment. Just hold on for a moment. Those of you who are watching on YouTube. Uh, Wait, guys, wait. So I'm sharing my screen, and to share it on YouTube, it is just taking like a little bit of time. Give me a moment. Yes. Now I hope you are able to see my screen. Okay. Good. So we will start with a quick revision first, what we have discussed so far, and then we are going to talk about what is strongly connected components. So I hope you had attended my previous class, or even if you have not attended, it's fine. But you know what is directed acyclic graph and how we can find a topological ordering of it. Um, I will do a very quick revision of what we have done. So a DAG is a directed graph such that there is no cycles. For example, here I have drawn 5 examples. Out of these, the ones with uh, corresponding to whom we have a green tick, they are DAG, but the others are not a DAG, right? So we took an example of a DAG where you can have a complex software which uses a multiple modules, and there can be interdependency between them. So in the right side, you can see the dependency graph. That means Django Mongo engine requires Django, and Mongo engine requires MongoDB, Django requires Python, OpenOTP, GCC. They were just like hypothetically selected as modules, but this is something that you need to understand. Now, main question is, how do you install your dependencies on your computer? Because if you directly go to install Django, then it will fail, because it will tell you that okay, Python is not installed. Or if you want to go to install Mongo engine here, like you can see, then it will give you requirement not certified, MongoDB not found. So therefore, we need basically a particular order in which we want to install these softwares. Now, since there are no cycle, it is always possible to find order. So the order in which we are going to install is called the topological ordering. Now, to find topological ordering uh, or topological sorting, what we do in the DAG is we basically prove that in any directed acyclic graph, there is always going to be at least one vertex which doesn't have any incoming edges. For example, in this graph, you can see node number 1 and node number 6 have no incoming edges. The only outgoing edges they have, right? So we proved that like this is always true. And once we proved that, we also proved that if even if you remove some vertices and lead edges from a DAG, then the resultant graph is still a DAG. It cannot contain cycle. We proved all this by contradiction. So we know that, and now in this algorithm, what we do? We pick those nodes which doesn't have any incoming edges, and we mark them that okay, like this guy is like the top level software, and nobody depends on this. So we are going to install this guy at the end. Okay, so we are going to install this guy at end, because all the other requirements that it has must be installed before we install this guy. So this will be installed in the last. So you can here see the installation order from right to left, and node number 1 is in the beginning. So that means this is going to be installed at the end. So, and then like after we choose that, we remove that node from the graph, and we also remove all the associated edges with it. Then in the resulting DAG, we repeat this thing as long as we have any node in the DAG. So you can see the algorithm, repeat the following until there are no nodes remaining. Find a node which does not have any incoming edges, insert it into the topological sorted array, remove this node and all the outgoing edges from it, right? And you keep on repeating this. So the resulting order that we get is a topological sorting. We saw that the time complexity is linear for this algorithm. Then we also saw that we can do a DFS based implementation of this, because and how do you do the DFS? Like you basically do post order traversal. So whenever you are at a node and you want to do DFS, then you list the nodes from all the children that it has first, and then after everything is over, then you mark that as in the DFS order. So why this works? Because see, like these are dependency graphs, and if you are at node number 3, for example, then to install software number 3, you must have node number 4 and 5 installed, and so on, like so in a DFS order. So what you do? Go to one of the branch, let's say like to 4, and you install software 4. Now again, to install software 4, there will be some requirements which are already taken care of because of the DFS. So after software 4 is installed, you go back and install software 5, and after 4 and 5 is installed, you see that all the requirements are satisfied, then you install 3. So this is a post order traversal. And if you do this, then like it also produces a topological ordering of the vertices, because this is a more I mean, like for some people, it might be easier to visualize why this works. Now, both of them are topological ordering, but one key thing to notice is the order in which they were giving you the nodes are just like in a reverse order. So in this case, like the topological ordering is from left to right. That is, node number 1 should be installed last from left to right. On the previous one, it was from right to, but that is not a problem. You can just like always reverse the topological ordered array. right? So to basically this also means that you are doing you are basically listing the nodes according to the exit time, this DFS based approach, right? Like you are doing this thing according to the exit time of in the DFS, right? You are doing the, because see, like um, whenever you are doing a DFS from 3, and if you go to first the child of 4, then after 4 is exited, that is like DFS from 4 is over, then you go to 5, and then like after it is over and every other child that it has is over, then only you are marking the 3 is finished. So that is a precisely what exit time is, if you remember what we had discussed in our second lecture on DFS, right? So we are basically ordering them according to the exit time, and this ordering according to the exit time basically gives you the topological ordering, right? Simple. We took some examples also. Then we saw one quick example where we wanted to count the number of paths between two vertices u and v, how we can do that using the topologically sorted array, right? So we solved that problem. Now the next question that we have at our hand is we want to discuss how do we find strongly connected components. Okay, is there any doubt in whatever we have discussed so far? I'm stopping for 1 minute. Yes, Sarma, session has started at 3 p.m., but the content started at 3:05 p.m. So not we were not basically late. Can I do CP with Java? Siddharth Padhi, yes. Many people do CP with Java, no problems. Just that, like, who knows C++, then it is more convenient in some most of the cases. So people prefer to do this in C++ if they are aware of. But which order is standard, sir, for topological? The second order is standard, I would say. Although there is nothing like standard or non-standard. Sharshita, the second option, right? Like in which we order the nodes from in which we are going to actually install the software from left to right, the DFS one. Okay, so you can say that like that is more useful. It's not that like this is more standard in most cases, but it's not a problem. You can just like reverse the array, right? That is a simple task. Cool. So let us now go and define what is strongly connected component. So we have defined a connected component in a graph, right? So in a normal, in an undirected graph, a connected component is nothing but basically if each of the nodes is reachable from each of them. And if you draw the graph on pen and paper like this, then one can clearly see that this guy is a connected component because each of node is connected with each other. But how do you define connectedness if the edges are directed? How do you define connectedness if the edges are directed? If you have given a graph like this, will you call a connected? Um, is someone saying that this should be called connected? Now, somebody was so basically this. Some people said that, sir, okay, so let me define connected by saying that if for each pair of vertices u and v, if there is a path from u to v, or if there is a path from v to u, either of these two cases or both of the cases, if any of these two cases are satisfying for each pair, for all pair, then I will call that a connected component. Somebody was saying something like this, right? Um, so maybe like they would like to call. But what happens in this graph? This is a graph. Okay. Um, does it feel like connected? The if the edges were undirected, then it would feel like okay, this is connected. But if you clearly see that between these two pair of vertices, neither there is a path from here to here, neither there is a path from here to here. So if you try to like call that a connected component, I mean, like I don't know, like how would you define it? But to me, it feels that okay, like this is a very poor definition. This would be a poor definition for defining connected component. Um, or I don't know, like some people may call this connected component. So how then connected components are defined in directed graph? So let us come back to the original question. Okay. Directed graph is strongly connected if and only if between each pair of vertices u and v, um, there is a path from u to v. Each pair of ordered vertices, let me call them. Ordered in the sense, like, yeah, there has to be u to v and v to u is different. There has to be a path. So this guy is called strongly connected. Now, for a moment, we uh, need to see two things here. One is we have an additional word called strongly, which was not there in the normal definition of connected component. So now this is strongly connected. We are emphasizing that this kind of definition is very strong, that it's not just like one-sided connectedness, but like it has to be like each pair of node is connected with each other pair and so on. So this is one strongly connected. Okay, and there is a path from u to v for each pair of so basically that's from where it is going. And also for a moment, let us like forget what this connected component is. So let us focus on a strongly connected directed graphs. Then the component part is same as it was in the undirected graph. Okay. Now examples. So if I have some examples, can you guys tell me which of them are connected and which of them are not? Maybe this is like written just too close, so let me write it here. Which of them are connected and which of them are not? In this node you can, I will only take this for this example, level the node. One can clearly see that there is a path from 1 to 2, there is a path from 1 to 3. uh, where is the path from 1 to 3? The path from 1 to 3 is via 1 to 2, right? So there is a path from 1 to 2 to 1 to 3. Then there is a path from 2 to 3, and then there is a path from 2 to 1 as well. And then similarly from 3 to 1 there is a path, and from 3 to 1 to 2 there is a path. So between each pair of vertices you can see there is a path. So therefore this guy is a connected component. This guy is a connected component. But in this graph, in the second graph, you can see that there is no path from there is no path from 1 to 3. There is no way to go to 3 from this. Therefore this is not a strongly connected component. This guy is 1. Now, can you guys tell me for the rest of the 4 graphs whether they are connected component, strongly connected or not? 35135. Somebody is saying this is strongly connected. Yes, this is strongly connected. People can verify that. Now this guy is not strongly connected because there is no way to go from the bottom node to the top node. Then clearly this guy is also connected, strongly connected. Each pair of node is reachable from each other, and this guy is not strongly connected. So yeah, I hope this is clear. If there is any doubt, let me know. Piyush Agrawal is asking, sir, can we do topological via BFS? So, Piyush, the first algorithm that we have talked, it's sort of like similar to the BFS implementation. Uh, so, if you would like to call that using BFS, then okay. If not, then maybe not. So, it is just like BFS. In BFS, what you do from each node, you basically relax each of the other nodes that is directly adjacent from it. But in this case, what you do is you only relax those nodes whose n degree is 0. So there is only slight change in the criteria. Otherwise, implementation wise, this is exactly same as BFS. So if you want to call that as a BFS, then okay. If not, then no. Sir, is it necessary to have a cycle containing all vertices? Harsa, you tell me. Like, do you think this is your requirement? Um, I think that may not. So you are basically saying, sir, is it necessary that there should be a very large cycle which contains all of the nodes? I think that may not be necessary. So try to think of some cases where it is not necessary. Let us try to think some cases where that is not necessary. Let me try to find here cycle. Yes, I think one example could be. If this is the case. I'm trying to think if it is a strongly connected component or not. Yes, it feels that this is a strongly connected component, this new graph that I have drawn. Um, can somebody confirm that this is indeed a strongly connected component? Which of them are connected is using this guy is to you, and this guy is connected to everybody else. So this guy is also connected to everybody else. Yeah, I think this is a strongly connected component. This is also a strongly connected component. But here I don't see any large cycle for which each of the nodes is a part of. Okay. So Archita, does that convince you that that may not be necessary? There is a cycle, but I thought you meant that there has to be a very large cycle which contains all the nodes. So that is not the case. There has to be cycles. If there are no cycles, then it will be a DAG, directed acyclic graph. Then there will never be any strongly connected component. So there will be cycles for sure. If there are no cycles, then it will be a DAG. Like that is what we have studied yesterday. So, and in DAG there are no strongly connected components. Each of the individual nodes are. So I thought you meant that there has to be a large cycle of which each of the nodes are a part of. So that is not true. So yes, let me then make a note of it also. there has to be a cycle. Has to be cycle. Now, why this is true? Because if there are no cycles, then so assume that there are no proof. Like if you want a like quick short proof, then proof is assume the contrary, right? So if there is a since if there is a path from node U to V, some particular node V, then for it to be a connected component, there has to be a path from V to U as well, right? And since the same path cannot be true from U to V and V to U, so if there is another path from V to U for it to be strongly connected component, then you have a cycle here. So this is like very obvious. There has to be at least one cycle for sure, but there is no guarantee that there will be a very large cycle which will contain all of it. So a very quick proof was that. Not of n nodes in cycle we can't repeat edges, sir. Oh, if you repeat the edges, then same node will come like multiple times, right? Same node will come multiple times. Then is I mean, obviously possible because it is given in the graph that you are allowed to go from each node to each other node. So from one you will go to two, from two you can go to three, from three you can always go to four, from four you can always go to five, and so on. So you can always cover that like that, but that won't be like a simple cycle. That's not a simple cycle, right? In that fashion, yes, there has to be a cycle everywhere. So I mean, like the so for example, what you say? Is there a big cycle here because it is connected? No, right? Like you won't call something cycle for this example, right? Because you will say that, sir, from 1 to 4 I can go, then from 4 to 2 I can go, then from 2 to 4 again I can go, from 4 to 3 I can go, from 3 to 4 again I can go, and from 4 to 1 I can. So this is a big circle, but this is not a like simple cycle like that, right? This kind of thing which you felt that is a cycle is actually called a tour. Okay, so this is a tour in a graph and not a cycle. There is a separate term for that also. It's called a tour. Okay, nodes and edges are allowed to repeat. One of the most common example for this the Euler tour in a tree. Tour also exists for a graph, but like this is very uh, useful thing that like you always do for finding LCA and doing heavy light decomposition and many other things. So this is one example. So tour is basically where nodes and edges are allowed to repeat. Okay. Any other doubts? So now now the very basic question: given a directed graph, how to verify that it is strongly connected? How do we verify whether it is strongly connected? If you are given a directed graph, how do you verify whether it is strongly connected? So the obvious solution is you do a you do a DFS or VFS from each node, right? You do a DFS from each node. So, but then the time complexity for this will be order V into V plus E, because you have to do the DFS from each node, right? Then how do you solve this problem? How you can do this thing in a better complexity? Find a tour of all vertices. I mean, what do you No, like just saying that find a tour of all vertices is not correct. How do you find that tour, right? Sachin Kumar is saying take reverse graph, compute DFS on reverse graph and graph. Mhm. Okay, Sachin, if you think so. Is there any argument to support why this should work? Why will this work, Sachin? Tell me. Because when we traverse, we know the ancestor of each vertices. Um, okay, I give you guys 2 minutes to think about this problem. And if you have anything on your mind, please write it down in the comment. Detect the biggest loop by DFS. Then we do DFS for only the nodes not in the biggest cycle. Harshita, first of all, detecting the biggest loop by DFS is not a simple problem. Um, then even if you do, then like we do DFS for only the nodes not in the biggest cycle. But it's still like it can be the biggest cycle is small. There are like many small cycles or something. First of all, the first problem itself is difficult. Then also still you are doing a lot of DFS. Harshita was right. I think in large cycle argument, see Sachin, what actually will happen is see, if I give you a this kind of problem where there are like many small loops like this. Okay, many small loops like this, and there is one large loop like this. So each of these contain square root n nodes. Okay, the square root n nodes, and then this large cycle will also contain, of course, like square root n nodes in total. So the largest cycle you will find is still square root n nodes. So the rest of the nodes that remains is n minus square root n. And if you do the DFS from all of them, so n plus m, then it is still basically n into n plus m, because like this square root will be ignored in front of n. So no, like that is not a good algorithm. I mean, like it will improve your solution a bit, but it doesn't improve it significantly or in a amortized way. First of all, and the second problem itself is how do you find the biggest cycle? That is not an obvious problem. Finding the biggest cycle in a graph is not obvious. Let's assume how will you make it most of a large cycle. Sachin Kumar, I just gave you a counter example that no, it is not necessary that we must have a large cycle. In I gave you two examples, right? The first example proved you that no, all nodes are not part of a large cycle, and the second example I gave you, the cycle size cannot be too large; it can still be very small, like of the order of a square root n. So all those arguments fails. Okay, so let us keep this problem for a moment, and we are going to discuss about that algorithm, and then you will realize that oh, the Kosaraju's algorithm not only detected the whether a graph is complete, strongly connected or not, it if also gives you all the strongly connected components in linear time. So we put this guy in on hold for a moment. Okay, and let us now see what happens. Let us take any directed graph which is not strongly connected. Okay, so for example, this itself is a DAG, there are no cycles. So let me take another example. Now this is not a strongly connected graph, right? Not a strongly connected graph. So let us observe some properties of this graph. Let us try to find the components of this graph which are strongly connected. So strongly connected component is not nothing but uh, subgraph or a component, subgraph or a component of the original graph in which uh, each node is connected with each other node, right? So basically, that particular component is strongly connected. Okay, so basically, if you have a subgraph where each of the nodes is connected with each other, that subgraph in particular is strongly connected, then we call that as a strongly connected components. um, okay, now let us observe something about this. Who are the cycles here? Or who are the strongly connected components here? Who are the strongly connected components? I can notice one strongly connected components over here. I can also notice one connected components over here. Are you guys able to notice anything else? Like, are there any more connected components? Right, so these are two connected components, right? Now I have taken a simple example where it feels that okay, the connected components are always going to be in a cycle, but that is not always true because I have already given you counter example to that. But in a simplistic case, you can see this as a small connected components. Now let us do one thing. Do what? compress each connected components into one vertex representing that connected component. Okay, so what do I mean? So in this original graph, let us modify the graph in such a way that we compress these vertices and we keep only the sample nodes. So for example, here I am only writing 3, but this 3 also represents all the other nodes, and the rest of the nodes are kept as each, and the edges are also kept as each. But this 3 contains 1, 2, and 3 with it, and we use some other color here. And this actually contains 6, 8, and 9. Okay, so can you say something about this reduced graph? This is the reduced graph. Can you say something about this reduced graph? Claim. The reduced graph so form is a directed acyclic graph. This is my claim. Clearly, in this example, this is a directed acyclic graph. But in general, I am saying that if you compress all the strongly connected components into one representative node, and the compressed graph or the reduced graph thus formed is a directed acyclic graph. Okay. Now, let me also emphasize here that when I'm talking about a strongly connected component, they are the maximally strongly connected. Connected components, I mean maximal strongly connected. What does that even mean? So I mean, the way we have defined a strongly connected components, it is clearly possible that node number 2 is itself one particular strongly connected component. This itself is a strongly connected component, right? And this itself is a connected component. So if you do like that, then nothing will change. The graph still remains the same. So what I actually mean is, not only don't pick like each individual nodes one by one and say okay they are strongly connected, although they are, but what actually I mean is pick the maximally connected components, right? Like this is the maximally connected component, the strongly connected one. See, if you add any more node to it, it will never be a connected component, right? A strongly connected component. So pick those set of nodes such that it forms a maximally strongly connected components. So try to keep adding more and more nodes to it. If it is possible to add more nodes, keep on adding it. When you exhaust and when you see that no new nodes can be added in that connected component, then that is a maximally connected component. Okay, so similarly here, this is also a maximally connected components. Okay, I hope you understand this. And this 6 here represents that particular node, and this 3 here represents that particular connected component. Now the claim is, we still need to prove this claim. Needs to be proved. But do you agree that like this will always be true? So we store the nodes that we know are strongly connected. The new nodes, if connected to any of the nodes, it added to the list. We store the nodes that we know are strongly connected. We store the nodes that we know are strongly connected. Then new node, if is connected to any of these nodes, It added to the list. Yes, that is what I meant by saying when I said maximally connected components, Harshita. If that was in that context, you said. Sachin Kumar saying not SCC. No, no for what? Like, is this claim false or what do you mean by no, Sachin? Could you elaborate? What does yes mean then? Like, do you say that like this claim is true? Claim is false, then like can you give me a counter example? Harshita, we are going to find all these maximally connected components today, so don't worry. But for now, let's say somehow they are found. Then, like, is this claim true? Sachin is saying the claim is false. So therefore, I am waiting for Sachin to give me some counter example to it. So counter examples would be given such that you are giving me a directed graph, and when I compress all the strongly connected components into one node, yeah, I'm giving you 2 minutes. It is a good exercise. Like all of you take 2 minutes to think about this. ADG, a directed graph, oh, a DAG only if the graph is not strongly connected. ADG only for graph is not strongly connected. No, I mean, it is not that, okay, the graph is either strongly connected or DAG. Like, this is not the case. So, for this example that I have given, this example here, uh, this guy, this whole example, here you can see that this is neither strongly connected, neither DAG, right? So, this has some components which are strongly connected. This can also be true. So my question here, you can clearly see that compress each connected component into one vertex. For example, 1 and 2 and 3 here was strongly connected. So I compressed them into one node and call this 3, and this 3 is representative of each 1 and 2, 3. Similarly, 6, 8, and 9 were compressed into one node 6, and here you have this situation. Then this is the reduced graph on the left side. So this reduced graph, I am saying, this reduced graph is a DAG. That is my claim. So can you guys confirm that this is true? If not, then can you give me a counter example where that may not be true? Sachin is saying it is true. The compressed version will always be DAG if it's not strongly connected. Even if it is strongly connected, then also it will be compressed to one side. So one node can still be called as a DAG. We can still call one node as a DAG. So in that sense, yeah. But if you don't want to call one node as a DAG, then okay, maybe not. Let me try to argue something. Strongly connected when you compress them. So let us take this compressed graph. Okay. So proof. Let us take the compressed graph. The compressed graph and assume the contrary. That is, assume that the reduced graph has a cycle. Has a cycle. It is not a DAG, that means it has a cycle, right? Take that cycle. Consider that cycle. Okay. So this is the cycle, right? This is the cycle. There has to be a cycle, so I took like any of the cycle because it is not a DAG. So if it is a cycle and each of these is strongly connected component, if this is strongly connected, this is also strongly connected, and each of them are strongly connected components, right? Because in the reduced graph, each of them are strongly connected, and we have a cycle. So what I am claiming is, obviously, in such a case, the complete set of vertices on this cycle form one strongly connected components. Why? Because you can since like if you can, so this cycle itself is a strongly connected component, right? H, the cycle itself is a strongly connected graph, right? So if the cycle itself is a strongly connected component, then if you pick any node from any of this connected component and any node from any of them, then you can always take this path to reach here and you can always take the other path to reach there, right? So if you have many strongly connected components which are forming a cycle, that means this whole guy is strongly connected, right? This complete thing. So therefore we arrive at a contradiction that the compressed graph had maximally selected selected um, selected SSH. SSH, right? So what I mean is, let's see, like when I said that the reduced graph, then I mentioned that these strongly connected components has to be maximally selected. That means you cannot just like pick one individual nodes. You need to pick as many nodes as possible. So in this case, why would you pick this guy as a strongly connected component when you can like pick all of them together as a strongly connected component? So that is a contradiction. So therefore, hence proved, right? Hence proved that the reduced graph is going to be graph will be DAG if the strongly connected components are selected maximally. Is there any doubt? If there is any cycle in a graph, it is going to be SCC. So it is contradictory. It's true. So Sajin, like, is everything clear or is there any doubt? Clear. Okay. If anybody has any questions, please let me know. Also, you can ask your questions on YouTube. One example of SCC and a compressed graph, sir, please. So I have already given you one example here. Do you want me to give more examples? Then I can give you one more example. Okay. I think I have given the same example here. One, two, three, 4, 5, 6. So here one can clearly see that this is one strongly connected component. I'm sorry, one small mistake I made here. And another connected component is here. There are two connected components, right? Indicated in green. Now the reduced graph will be this. You can call this 3 and you can call this 4, but actually this 4 is representing 4, 5 and 6, all of these nodes, and this 3 is actually representing 1, 2 and 3. And clearly this graph, this is or DAG, this is a DAG, right? Acha, SCC and compressed graph. So yeah, this whole thing, one, two, three, and the compressed graph will just like contain any node, and you can pick any node number, one, two, or three, anything as you use. But like it represents one, two, and three, all of them. Okay, so this is the strongly connected graph, and this is the reduced graph. Note that it has only one node, contains only one node. Okay. Yeah, so my claim is like give me any directed graph. I'm going to compress it in such a way that it is always going to reduce to a DAG. And I am calling a single vertex as a DAG also. That is also allowed to be called a DAG because there are no cycles in that. So yes, give me any directed graph. I'm going to find all these strongly connected components. I'm going to reduce them into one node, and that reduced graph will be a DAG. So that is what exactly what we have proved now, right? And I have also given a few examples for that. Okay, so now in the after the break, so now it is a time for a break. So break and for 7 p.m. Okay, and we are going to talk a few important things. The Kosaraju algorithm, and if time permits, then I'm going to talk about Tarjan's algorithm also. Tarjan's algo. Either we will talk Tarjan's algo or implementation of Kosaraju. Any of this. So these are two things that are still remaining after the break. Okay. Okay, now we are going to continue. So how to find the strongly connected components, right? Like that is the problem at our hand. Now first I will describe the algorithm, then we will see like why it works. According to exit time. Reverse the edges and do the DFS in the transpose graph in the decreasing order of exit time. Each DFS or BFS, any algorithm, each DFS or BFS, in the second step gives you each DFS or BFS in the second steps gives you the strongly connected components. Okay. So this is the Kosaraju algorithm. Very simple. You do a DFS order, you do a DFS and order the nodes according to the exit time, and then reverse the edges and do the DFS in the transpose graph in the decreasing order of exit time. And each DFS that you are or DFS or BFS that you are going to do in the second steps gives you the strongly connected components. Now, why does it work? We are going to take some examples. We have already taken one example. Let me pick that on. Yeah, so this graph one, graph like this. So this is one of the graphs, and one can label the nodes like this: 1, 2, 3, 4, 5, 6, 7, 8. Now we have seen we are going to visualize this algorithm first in the, let us iterate this algorithm first in the original graph, in this graph, and then we are going to visualize that algorithm in the reduced graph also, so which will give us the complete solution. So now let us start the DFS from anywhere. Let us start the DFS from node number 1 maybe. Okay, so if you start the DFS from node number 1, then you go to uh, the next node that is available to node number 3. From node number 3, one can go to any node, like maybe you choose to go to node number 4. Then from node number 4 you go to any node, maybe node number 6. From node number 6 you have multiple choices, but maybe you this time chose to go to node number 5. From 5 you see there is no option to go, so you mark this as exit time equal to 0. So this T represents the exit time. So there are nowhere to go from there. Then you backtrack from there. You come to node number 6. From 6, you have one more options to go. So you go to node number 7. From 7, you have more option to go. So you go to 8. From 8 you have more options to go, but you see that node number 6 is already visited, so you don't take that path, and at this point you realize that okay, the DFS from node number 8 is over, so you do that t equal to 1 here, and then you track back to node number 7. You see that there is no more options from here, so you mark that t equal to 2 here. Then you track back to node number 6. From node number 6 you see that everything is already visited, right? You had two options to go, 5 and 7, both of them are done, so you mark at this point okay, I am also done. So this is 1 2 3. Then from here you track back to node number 4. From node number 4 you see that like okay, whatever I have to do I have done and I am done. So then you again like track back. From node number 3 you still have two option left. You try to go to 5, you see oh, 5 is already visited, so you don't go there. From 3 you go to 2, you go to 2. Now from 2 you see you have to go to 1, but you see that 1 is already visited, so at this point you realize 2 is done, so t is equal to 5 for node number 2. From 2 you come back to 3. From 3 you realize that okay, everything is over, so at this point you mark t equal to 6 in this case, t equal to 6 in this case. So this is the DFS, and t represents the exit time, right? Now if you order the nodes according to the exit time, decreasing order of the exit time, let us do that. The decreasing order of the exit times of the first, you will have node number 3, then you will have node number 2. Oh, and of course like the exit time for this will be 7, node number 1 equal to 7, because from 3 you will come back to node number 1. Sorry about this. So first of all you will have node number 1, first node number 1, then 3, then 2, 1 3 2, and then you will have I think 4, right? You have 4, then you have 6, then you have 7, then you have 8, and then you have 5. So this is the order that you have according to the exit time, decreasing order of exit time. Decreasing order of exit time. Now can you see that if this were a DAG, then in DAG, if you order the nodes according to exit time, that is called topological sorting. Do you remember that? We had discussed about this. In a DAG, if you do this thing, then it is called, yeah, here. This nodes that is order and exit time. So if you order the nodes according to exit time, then this thing is nothing but the topological ordering if it were a DAG. But since the given graph right now is not a DAG, so we cannot say that it is a topological ordering, but like something similar has been done here, right? Something similar. So okay, now the next step is what? You again do the DFS in the same graph but reverse the edge, right? In the transposed graph of this. So let me redraw this. Here I will redraw. Oops, the edges has to be reversed, my bad. So the edges has to be reversed for this, 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 and this, and this. This guy will be equal to this. The nodes are still numbered as 1, 2, 4, 5, 6, 7, 8. Okay. So now in this graph, in the transpose graph, this, let us call this the transpose graph. You do the DFS in this order, right? We need to do the DFS in this order. So if we start the DFS from node number 1, try to do that. So we mark node number 1 visited, you go to 2, you mark this visited, from 2 you go to 3, and you mark this visited, from 3 you can only go to here, like which is already visited, so DFS is done. So what does the Kosaraju algorithm say? So when you do a DFS from each of the nodes in this graph, then this gives you a connected component. So therefore this is one connected component, right? According to Kosaraju algorithm. So 1 is marked visited, uh, 2 is marked visited, 3 is marked visited. So next node is node number 4. So from 4 you have to do the DFS. So from 4, if you do the DFS, you will realize, okay, so mark 4 as visited, mark 4 as visited, okay, 4 is visited. From 4 you have only one option to go, but that is already visited. So therefore 4 is a connected component, strongly connected component. Now the next node is node number 6. So you go to node number 6, and you mark this guy visited, and from 6 you have only two options, many options to go. 6 to 4, this is already visited, so from you go 6 to 8, you go here, from 8 to this, go 7, from 7 to 6, this is already visited. But like 4, no, you don't have a choice there. So these all these nodes that were visited in this step are forming another connected components. So 6, 7, and 8. The next node that remains here is the node number 5. You go to node number 5, you mark it visited, and you don't have any more options to go, because like both two options 3 and 6, but both of them are already visited. So this is another connected component. Can you see that this algorithm gave us the strongly connected components? So the strongly connected components are can clearly be seen. This is one connected component, this is another connected component, this is another connected component, this is another connected component, and which one can also verify from this graph here that we had built, right? So yeah, the Kosaraju algorithm worked in this particular case, but how can we say that this will always work? Is there any doubt in whatever we have done in this algorithm? Sachin Kumar is asking, sir, can you repeat the second part? So in the second part, we are doing the DFS in this particular order. So the particular order is decreasing order of exit time. So we do the DFS, and each DFS gives you a connected component. So when we first did the DFS from node number 1, 3, and 2, so if you do a DFS, then it will mark all the nodes which are reachable from that node to be visited, right? So from 1 to 2 is visited, from 2 to 3 is visited, from 3 to 1, both of them are visited. So this is like the first DFS, what it does, right? So the first DFS marks them visited. Is there any doubt in this portion why these nodes got visited? Then this is nothing but this is a very simple DFS algorithm that we have talked in the second class itself. And then after all these three nodes are visited, we go to the next node which is not already visited. So we go to node number 4. From node number 4, we have to do the DFS. So in DFS, we go to each of this child, but when we try to go to the child of 4, that 3 is already visited, right? So we don't do the DFS from there. If you remember the DFS algorithm, you only do the DFS algorithm for nodes which are not already visited. So therefore, in this algorithm, only this guy was explored, right? Only this guy. No new nodes were visited. So this is another connected component. But when we went to node number 6, all these guys got visited. So they form another connected component. In case of 5, this got connected component. Is it clear now, Sachin? Okay. So any more doubts? Let me know. Otherwise, I'm going to look at the same algorithm from a different perspective, so that it will start making sense to everybody. Okay. So the next step is, now we will look at this algorithm from the compressed graph point of view. Compressed or reduced graphs. kind of view. Okay, so for this, let us look at the same thing in the for this example itself, before we go to look at the general situation. This was the connected, this was the compressed graph, right? Like this was node number 3, this was node number 4, 5, and node number 6, and the edges were marked in this fashion. I think I will draw it in a 3, 4, right? It will be called 4. 4, there will be edge shape. So this is the graph. Now please note that although this is just like one node, but this is actually a connected component. This is also a connected component. So when we first did the DFS, and we ordered the node in the exit time order, then, and we know that this guy is nothing but a DAG, right? We have proved that this guy has to be a DAG. So this is a DAG. Now, when we ordered the nodes in a exit time order, then that was a topological ordering, right? So that was a topological ordering. So the topological ordering was amongst all these nodes, they were ordered according to the exit time, right? So if we only concentrate on these nodes, that will definitely gives us the topological ordering, right? So let me write this. If we focus only on the reduced graph, then the nodes according to decreasing order of exit time, focus only on the revenue gives you the topological sorting, topological ordering, right? So one can also note down the exit time for these particular nodes. So for node number 3, exit time was t equal to 6. For node number 5, the exit time was equal to 0. For node number 6, the exit time was equal to 3. And node number 4, the exit time was equal to 4, right? Yeah. So if you order them according to these node according to the exit time order, then the nodes will be 3, and then 4 and 6 and 5, right? Um, Decreasing exit time. So this is nothing but the topological ordering of these nodes. Okay, makes sense. Now in this topological ordering, how the edges are directed in the original graph? In the original graph, the edges are always directed in this fashion, right? Always from left to right, right? So node 1, edges are directed from left to right, right? Always, because we have already noticed this property. There cannot be edges in this direction ever in a topological ordering. We have seen that yesterday itself. So the edges are always directed like this, but never from right to left in this graph. Makes sense? So this is what the first step does. Now when we reverse the edges in this graph, when we reverse the edges in this graph, then what happens? It looks like this, it looks like this, it looks like this, it looks like this, and this is of course node number 3, 4, 5, 6. Now in the reversed graph, the topological ordering has edges only in the form of right to left, right? Because you have reversed the graph. So only edges like this are there. Make sense? So let me write that. Another note. In the reduced graph, the edges are from right to left, right? So this is the possible direction of the edge. Now tell me, if I start doing the DFS from this node, if I do the DFS from this node, then will it this guy visit any new node? No, because this guy will only visit edges which are on the left side of it, right? This guy is going to visit only nodes which are on the left side of it, but there are no nodes. There are no nodes on the left side of it. Therefore, whenever you start doing the DFS from node number 3, whenever you try to do the DFS from node number 3, it will not visit any new node. It is guaranteed that it will visit only itself, right? Because there are no edges from left to right, right? Make sense? And this can also be seen from the graph. Now, when you go to node number 4 in the next step, node number 4, then node number 4 can only were possibly able to visit node number 3, but 3 was already visited, but 3 is already visited. So therefore, when you do the DFS from node number 4, then no new node is going to be visited. Only node 4 is going to be visited, because any other node that were possibly were able to visit is already visited, because we are doing this DFS from left to right. Make sense? Now, in the next step, when you go to node number 6, then also, if you do the DFS from node number 6, no new node will be visited, because when you do the DFS from node number 6, then it were possibly 3 and 4 that could have been visited, but it is not allowed because they are already visited. So when you do the DFS from node number 6, again, only node number 6 will be visited. And in the last step, when you go to 5, only node number 5 will be visited. So in general, what happens is, when you have the topological ordering like this, and if you are at particular node U, and when you do the DFS from here, no other node will be visited. DFS, no other node will be visited. Right? No other node will be visited. But please remember, what is this reduced graph, right? But this reduced graph, each node represents a strongly connected component, but each node in this graph represents a strongly connected component. So that's why Kosaraju said that whenever you do a DFS, it is going to only find a particular strongly connected component in that graph, and no other strongly connected components will be touched, right? Now, if you basically look at this, although it says that if you do the DFS from 3, no other node than 3 will be visited, but actually this node is not only 3, but this is a connected component like this, right? This is a connected component like this, and even in the reverse graph, a connected component is still a connected component. So when you do the DFS from this particular node, then of course, like, all these nodes will be visited, right? All these nodes will be visited. So two quick things. One, a strongly connected component in the original graph is still a strongly connected component in the reversed graph, right? Now the second thing is, although in the reduced graph it appears that only one node will be visited in the DFS from these vertices, but in reality, all the nodes in that strongly connected components will actually be visited, will actually be visited, right? Because when you do the DFS from 3, this is actually like this. You do the DFS from 3, then like everybody who in this connected component is always going to get visited, and no other node will be visited, and that is exactly what we wanted, right? Like, we wanted to find a strongly connected component in this step, and we do find it. Similarly, when you go to node number 6, it will only visit these nodes and no other nodes, right? So I hope that this makes sense to you. If not, then let me take any questions that you have for me. Is this clear, guys? Is there any doubt? Do you want me to repeat anything particular? Let me know. But maximally strongly connected subgraph can be found by DFS in original graph too, sir. In the original graph too, no. In the original graph too, no. Why? Because in the original graph, if you do the DFS, see, so in the reversed graph, the point was, just a second. So in the original graph, the point was that in the topological ordering, the edges were from right to left, and you have to do the DFS from 3, then no new nodes will be visible. But if it were the original graph, then it were allowed that the edges are from here to here. So when you do the DFS from node number 3, it is possible that there's some other nodes will also be explored. But that is not what we want, right? So that is not what we actually want. Correct? We do not want that, because we want only nodes that are going to be visited in that particular DFS is the set of vertices which is represented by this particular node, which itself is a strongly connected component. And the point of reversing was because of this. So if we reverse this, then it gives you the topological ordering. Yes. And if you reverse this, then when you do the DFS from 3, it guarantees that no new nodes are going to get visited. Okay. So if you meant that, why does that answer? Only not topology. No, how? If you do the DFS from, for example, this were the original graph. If this were the original graph, and if you do a DFS from node number 4, then it will visit 4, and it will also visit 6, and it will also visit 5, right? So is 4, 6, and 5 a strongly connected graph? No, 4, 6, and 5 is not a strongly, and in fact, like, it will visit 7, 8, and 6, like all of this. So is this a strongly connected component? No, this is not a strongly connected component, right? Because it visits many other nodes also. I hope this makes things clear. Anything you want me to explain more in details, or is everything clear? So Harshita, I told you how reversing is helping us, right? Because if you don't reverse, then you are going to go out from that strongly connected component because of that. Like, did you attend my last class where I explained what is a directed acyclic graph and how in a topological ordering all the edges are ordered in a particular order, and there cannot be edges in both orders, right? So when I reverse the edges, then like it made sure that it is not exploring any new nodes, for example. That is what I was trying to explain. When I reverse originally in the graph, the edges will be in this direction, right? And when you do a DFS from this node, then it will visit not only this node, but it will also visit some additional nodes here. It could possibly visit, but I don't want that to happen, right? I don't want that to happen. What do I want to happen then? I want to have want to like reverse the edges so that no new nodes are getting visited. What I'm trying to do is basically when I reverse the graph, then the edge direction becomes this, and then when I do a DFS from here, it is not going to visit any more nodes because like we have already visited exhausted visiting all of them, right? Like these guys are done, these guys are done, these guys are done. So yeah, that's the reason. That is how the reversing the edge is helping us. Oh, I think Harshita, You are not following my argument. I am like repeating the same thing, uh, the exactly same thing what you are asking. How do we guarantee that only strongly connected component part is there? We don't go out of, sir, because this is exactly what we are doing. So in this topological ordering, we know that the edges are always directed from right to left. And if I do a DFS from node number 3, then it is guaranteed that no new node will be visited, because any new node for them to be visited, there has to be edge, and the edge is always from right to left, and this is the first guy here. So there is no edge here from here to here. So how a new node will be visited? No new node can be visited. There are no new nodes there. So who will be visited? Nothing will be visited. That's why. Now once we know that no node will be visited, so then like we mark that like this guy is visited, right? Like this guy is done. So if you do a DFS from this, then only node number 3 will be visited. Now when you go to do the DFS from node number 4, then again the same argument follows. So from node number 4, the only possible node which can be connected is 3, right? Because the edges can be directed from right to left, and there is only one node in the left of 4. But this node is already visited. In DFS, we don't ever explore nodes which are already visited. So this is a very fundamental thing for DFS. We always visit nodes which are not visited, but 3 is already visited. So this edge is also useless. So we are not going to visit node number 3 from here. Then tell me, if you do the DFS from node number 4 and you cannot visit node number 3, then the only possible thing that you visit is node number 4. So do a DFS from 4, you visit only 4. Do a DFS from node number 6, you only visit node number 6 with similar argument, because from 6, the only possible nodes that you could visit is 3 and 4, but 3 and 4 are already visited. So these will never be visited. So when you do the DFS from 6, only node number 6 will be visited. But please note that these are although individual nodes in this reduced graph, but in the original graph, they are representing a set of nodes 1 and 2 and 3. Right. So when you do the DFS from 3, 1, 2, and 3 will be visited. Right. 1, 2, and 3 will be visited, but nothing more than that. So that is the argument. Harshita, is this clear? Any other questions? Yeah. So my question still remains. Um, so why do we reverse the graph? We could have also done that in this fashion, right? So now the question for you guys to think: what if instead of reversing the graph, we had visited the nodes according to increasing order of time, increasing order of exit time in the original graph itself. So please note that there are two stuff here. Like earlier we mentioned that we are going to visit in the decreasing order of exit time, and now we are going to visit in increasing order of the time, but in the original graph. Earlier it were reverse graph. So what is the situation? Will it work? Think about this. This is so you can take this as a homework problem. Okay. Will this problem work or will this solution work or not? Think about this. The next question is, before next question, let us like discuss a few more things. What will be the time complexity of the solution? Now, time complexity. Time complexity of the original graph. So, number first step is do a DFS and exit time or DFS to find the exit time. To find the exit time. The next step is order the nodes in exit time. Third thing is reverse the graph. Fourth thing is do DFS again. Okay. So what is the time complexity in each of these steps? Doing the DFS takes order n plus m. Let us say that n is the number of nodes and m is the number of edges. Okay. Um, define n is equal to number of vertices and m is equal to number of edges. Okay. So and then what is the order of the nodes in the exit time? So either you can sort them in a normal noob level way, like in order n log n, or now reverse the graph. So reversing the graph is nothing but order n plus m. You just go to the each of the edges and reverse them. Do DFS again. This is also order n plus m. Right. So what is the overall time complexity? The overall time complexity will be order n plus m uh, plus n log n. Right. So this is basically nothing but order m plus n log n. This. But this can quickly be improved. This can be improved if you improve this sorting, and this sorting can be improved to order n using count sort, or bucket sort. Why? Because each of the exit or in time is between 0 to n, right? And all of them are unique. So because the range of these numbers are very small between 0 to n and they are unique, you can sort it in linear time. So therefore, the improved time complexity will be so therefore, like this algorithm, this time complexity can clearly be improved to order n plus m, right? Or we call this as a linear time algorithm. This kind of algorithms. Okay, so time complexity is order n plus m, and sometimes it is also referred to as a two-pass algorithm because we are doing two DFS in two steps, two-pass algorithm. Now there is Tarjan's algorithm can solve in a single pass. But to understand the Tarjan's algorithm, I think it is a little bit less intuitive than this Kosaraju algorithm. Kosaraju algorithm is very intuitive. You can feel it. You can see why it is working and all. Although, like you can also feel for the Tarjan's algorithm, but it will take a little bit more time. And I thought I will be able to explain it in a little bit details, but unfortunately, I do not have enough time. So Tarjan's algorithm is another algorithm, and many people prefer this because it is quick to implement. You just like do one DFS and it will be completed. Okay, this is a two-pass algorithm because one two steps, like two steps of DFS. That's why. So time complexity is there. Now, what is the space complexity? Space complexity is also order n plus m because you have to store the graph and you are not storing anything else. You are just like storing all the nodes. So nodes is order n. So this is the space complexity. So this algorithm is very beautiful. It can solve the problem in order n plus m. Now, if you note that, if we revisit the question, if you are given a directed graph how to check if it is so we started with this problem, right? And we felt that we do not have any like good solutions. But now can you tell me how you can solve this problem now after we have discussed this algorithm? So we reverse the graph because it is a DAG, no, e plus b into e plus b. Yeah, please continue share order and yes, compressed graph is a single node. So that's what. So you run the basically Kosaraju algorithm. Algorithm and see if there is only one connected component. Now of course like we can basically the idea will be same, but any other idea will basically can be derived from this algorithm itself. But the point is you can do this thing in order, linear order time, right? So you can probably do like one or two DFS inspired from this algorithm itself, but the time complexity is going to be order n plus n. Okay. So is there any doubt? I'm still here for a few more minutes if you have any doubts. And also, I'm going to make a uh, announcement here. Sachin Kumar Tarjan's algorithm, I do not have time. I have to announce something, and that will consume 10 minutes, and we have only 10 minutes left. So therefore, unfortunately, I don't have the Tarjan's algorithm. You can read about it in the Wikipedia. But quickly, what it happens is Tarjan's algorithm, like very quick overview. So if you look at the DAG, then where is it? Where is it? Where is it? So, for example, when you do the DFS in this DAG, then you maintain two things. One, the path, and one, all the nodes that are in the stack so far. So in the DFS, what happens? You basically first start with a node, you keep on pushing those nodes into a stack, and then like you keep on like popping the nodes from the stack. So you maintain two things. You maintain two things. Let me write it first. Maintain the nodes which are in this stack. And the second thing you could maintain is the path in the DFS tree from the root to the current node. You maintain them, and then you can like see that if the Tarjan's algorithm plays in such a way that like these nodes are essentially going to contribute towards the finding the strongly connected components. So when you start from a node, like if all the nodes that are in that particular connected components are already visited, and then when you start popping out, then you see okay, you have some nodes left, so they are going to contribute to the strongly connected components. So please note that we really do not have enough time to discuss this thing in detail. So it is best if you see the Wikipedia page or like some other video where this algorithm will be given. Now to give you my implementation of this algorithm, let me find if you have this, then I will also send you the implementation. Kosaraju. This is the link to the implementation one can find. Okay, I have pinned the link. You can check that out. And also, like, there are many more algorithms that I had implemented. They are also in that notebook. If you want, then I can also share my screen with you guys. Do that. Okay, so I have this announcement that I have to make. So these are some of the batches that got launched recently, and you are not still like late to register in these courses. If you are familiar with Python but want to learn C++, if you are familiar with Java but want to learn C++, because C++ has certain advantages when you do competitive programming because of its very robust and powerful STL and the speed with which it works. So if you want to learn C++, then these are the courses. Okay. And then there are two more courses, Prodigy. These two courses are on data structures and algorithms. One is advanced level, one is more comprehensive. The comprehensive one contains all the details from the very basic, like binary search, basic data structures. Advanced one like skips the basic stuff. Okay. So you have these two guys launched on 27th, and these two guys launched on 26th. Okay. um, this is a 10-month course, as you can see, and this is a 6-month course, as you can see. So this is more comprehensive, and this Prodigy course omits some of the data structures and algorithms like binary search and all. But these two courses are both 8-month courses, and if you want to transition from Python to C++ or Java to C++, you could enroll in them. Now, I always emphasize about this structured learning path. Okay. So structured learning path is very important, because when you are in college, you do not know what is the right thing that you need to learn and how much time you need to spend on uh, some particular algorithms, right? That which algorithm to learn, how many problems to solve, and so on. Especially at the time of COVID, this has become even more hard. You are not even with your friends. Although I was lucky to have a good friend circle where we would practice these things. But still, a structured learning path is always very helpful, and this course is intended to provide you that. Now, also in Unacademy, you can take one subscription to join all the batches or courses that you have. But when you take the subscription, don't forget to subscribe using my code Triveni692. Okay. So when you use my code Triveni692 to subscribe, you get a 10% discount. You get 10% off. Now this helps you in compete in contests like ICPC, Code Jam, and many other contests. Now it also helps you crack interviews, which is an important aspect for many people. Um, and the educators are very good. Like, they are the one of the best educators. They have done very well in whatever they have done. So you don't worry about the quality of the educators. You can see in the next page that how who are these educators. What does the course provide? It provides you live interactive classes like these, where the educator will be teaching and the learners will be there online. You can ask your doubts and everything on the comments, and the educator will help you resolve your doubts. Not only that, there will be a dedicated doubt support. There are Discord channel, there will be forum, there will be a lot of TAs which will be helping you answer your doubts even after the classes. There will be dedicated doubt solving classes and so on. Now, this is where what is, I feel, a very important aspect of the structured learning path. Here you will have curated problems and picked problems that will be added to the contest page, and one can practice these problems from the contest sites. And then, like, these problems will also be discussed in the doubt solving classes. Okay. So this is what these classes has to offer. Now, what are the content that is covered in these batches? One can see this. This guy is going to launch on 27th, which it includes almost all the basic things that you need, like sorting, searching, concepts, and problem solving, basic data structure, additional concepts, number theory. You can see like greedy algorithms and all, recursion, discrete mathematics, graph algorithms, computational geometry, advanced dynamic programming, segmentary, and so on. But this Prodigy course omits some of the earlier structure, and it will jump onto square root decomposition and related problems, number theory, recursion, DP, segmentaries, graph algorithm, discrete maths, and so on. Now, who are the educators? You can clearly see on the screen some of the educators you might also recognize by their face. They are world finalists, grandmasters, alumni of top product company, and so on. All right, and you can still see more of our educators here. So see Tanuj Khattar, world finalist, Pulkit, grandmaster. You can see all of them on this screen, and many more are joining every day. But all of the educators are very high quality, as you can see from this screen. Right, whatever they have done it pretty good. Now, as I mentioned earlier, also you should use my code 32692 when you take the subscription, because that will give you 10% off. So, for example, if you are subscribing for 12 months and if you are getting 54% off, if you use my code, then it will give you 10% more. So you will eventually get 64% off. So that's why like you should use my code 32692, and you also need to look at this referral discount is not permanent. It is temporary and it might be reduced to smaller value sooner. So if you think that this is a good time for you to take the subscription, take it as soon as possible. Don't procrastinate, because then you that is chances that you will lose out on the discount. Okay, so this is all, guys. I hope you enjoyed the class. And tomorrow, what we are going to talk? Tomorrow, we are going to talk about, again, we are going to come to undirected graphs, and we are going to talk about cut vertices and cut bridges. Tomorrow is the last class in this micro course. We are going to see cut vertices and bridges. This may sound complicated or something to some people, but this only uses the very basic simple stuff called the DFS algorithm. Simple DFS. So see you guys tomorrow, and tomorrow is the last class, as I mentioned. So bring in all your friends, and tomorrow's class is not related to today's or yesterday's class, so that will be pretty independent. So you can bring in all your friends tomorrow. If you have any doubts, I am still here for 1 minute.